Okay, good morning. So, can anybody tell me what we're doing? Anybody got a sense of what the story is at this point? If you don't, that's fine. That's my fault as a storyteller. Zoe, you look like you want to. Your hand is just about to raise? No.
I mean, I was just thinking like quadratic functions.
Quadratic functions, right? And what are we doing with them? Optimizing them. Yeah. So that's really the story. Actually, we're kind of giving you like a foreshadowing of what is going to happen a lot in calculus, which is optimization. And so we don't have the tools of the calculus, and so we're going to basically show you some things of what you could do if you didn't have calculus. And for for us, what we can do is one thing that we is sort of like maybe the first thing that you could optimize that's not trivial is parabola, right? So for parabolae, you can find where they reach a maximum if they're downwards pointing, or if you can find where they reach a minimum if they're upwards parabola. Right, and so we finished up last time with this one example, which was this one: f of x equals negative 3x squared plus 2x plus 1, which we used the completing the squares on to show that it had this form: negative 3 quantity times this guy here. Okay, so and if we multiply that out, if we distributed, we could write that as this plus 4/3. So that's where we finished up, and I think that might have been a little bit confusing. So let me just say one thing before. So let me say one thing that I probably should have said before. Let me introduce one more transformation. So one more transformation. Okay. We saw like translations and we saw reflections. One thing that we didn't see is something called the dilation. That's actually one that was missing, and when I introduced translations and reflections, I thought, oh, it's odd that we're not doing dilations here. Let's introduce dilations. You can also think of dilations as something called scaling. Okay, so so suppose you have suppose f's graph looks like this. Looks like the following. So suppose you have some function f. Okay, and f looks like this. So here's 1 and here's negative 1. 1, 2, 3, 4. 1, 2, 3, 4. So f looks like this. It starts off at 0. It goes up to 1. It comes back to 0, goes down to negative 1, and comes back up to 0. Okay, so it looks like it's what's called a sawtooth graph. Okay. And from then on, it repeats. Okay, so it's what's called a periodic function. It repeats, it has a period of repetition. So from here, it does the same thing, comes up to 1, comes back to 0, down to negative 1, comes back up to 0, and so on and so forth. Right? And repeats also in the reverse direction. So down to 0, back up, down to negative 1, back up to 0, up to 1, and so on and so forth. So you've got this sawtooth graph. So one thing that we didn't do was multiply the function. So suppose I have another function, and it's just a multiple of f. Okay, take a few seconds and draw what that graph would look like. What would the graph of g look like? So this is y equals f of x, I'd like you to draw what y equals g of x looks like. Okay, turn to somebody nearby and show them your picture. Okay, would somebody like to tell me what it will look like? What will it look like? G. Anybody? Lana?
So instead of
That's right. So everything will get multiplied by 2. So at here, 2 times 0 is 0. The y value doesn't change, right? Because what you're changing here is the y value, right? Y is now going to be twice f of x, right? So you actually go up to here. Here you go down to, you're back down at 0, and here you're at -2, right? So you've increased the amplitude, right? But you haven't, you're not affecting the x values, you're only affecting the y values, right? So come back to 0, like this, and so on and so forth, right? Okay, makes sense? Right? And if we created another function, say 1/2 f of x, well, then you would just be squeezing it down, right? If I multiplied by a number less than 1, then I'm squashing it down by 1/2. Okay. Right. So this is kind of vertical scaling. Okay. What if I create another function? Let's say. J of x. J of x is f of 2x. Okay, see if you can draw that function. Okay, talk with the neighbor. Okay, anybody want to say what that will look like? What does J look like? Maybe choose a different color. It's almost the same. It's like my daughter's soccer team. They just played a team that their color was this green color, and they played a team that was this yellow color. They're almost indistinguishable. Yeah. So what should this one look like? F of 2x. Anybody want to say? Anyone want to venture a guess? Aaron, are you raising that? Let's see. Let's think about it. So when x is 0, you're going to get f of 0, right? When x is 1, you're going to get f of 2, right? So f of 2 is actually 0. So actually you come down here, right? What about f at when x is a half? When x is a half, you're going to get f at twice a half, which is 1, right? So it'll actually come up here like this. So it's not a stretching this way, but actually a collapsing this way. And you're squashing this way. So another way you can think about that in terms of time is that for this function, time is traveling twice as fast, right? So it's doing things twice as fast as the other guy, right? So if this guy's going at this leisurely, like I'm going to come up and come down and come back up and come down. You know, every four steps I complete a period, right? In this case, it'll be every 2 steps that you can complete a period, right? Because by the time you reach 2, you're doing what the other person has done at time 4. Okay. So it goes like this. Okay, so it'll be twice as fast. And if we had created some other function being f of 1/2 x, then that would be stretching it out, which that would be the stretching out one. But you'd slow down time by 2. So you've dilated time. Okay. So you can see why these are called scaling or dilation, right? You're sort of dilating things, or you're scaling them to a particular scale. Okay. So okay. So coming back to this guy here, right? This is where we finished up. We've got this function, right? And what is it? Well, it is the unit parabola, right? It's the unit parabola shifted over by 1/3, right? So it's this is 1. It's been moved to the right by 1/3, right? The time is slowed down by 1/3, right? And then it's multiplied by negative 3, right? So it's flipped over, right? That's multiplying by -1, and then you multiply it by -3, so you stretch it out this way, right? Multiplied by -3, multiplied by 3, so it becomes a sort of faster, skinnier version, right? And then you move it up by 4/3, right? You move it up by 4/3, and it's right here. This is 1, so it's 2/3. Okay, so you end up with this skinny parabola going downwards like that. Okay, is that all right? Okay, so right, and so the question was, where is this function optimized? Well, you see that it's got a max, doesn't have a min, right? Goes to negative infinity. Doesn't have a min, but it does have a maximum value. So has a maximum value of 4/3. And that occurs, and an axis of symmetry at x equals 1/3. Okay. Okay. Do you all want to try an example along those lines? Maybe it's good. Or is that enough, or do you want to try an example? Try an example. Okay. So here's an example for you to try. F of x equals 2x squared minus 4x plus 11. So first off, let me ask, is it going to have a max or a min? It's going to have a min, right? Because it's an upwards parabola, right? It's got a positive number on the square, so it's going upwards, right? As you go off towards infinity, the x squared is going to dominate, right? Okay, so it's an upwards parabola. You know it's going to have a min. So the question is, what's the minimum value? What's the minimum value? Okay, so take a couple minutes to do that, and I'm going to go get some more chalk. Okay, talk with somebody nearby. Okay, how do we simplify this? F of x is 2x squared minus 4x plus 11, right? So probably it's easiest to factor the 2 out at the beginning. X squared minus 2x plus 11 halves, right? And then what do we do with this? Completing the square, so we take this guy and we rewrite it as x minus 1, thank you, right? Minus 1, right? We take that thing and change it into this thing, and we've got this plus 11 halves here, right? And so that turns into twice x minus 1 squared, so we have a plus 9 halves, which we could leave that way if we felt like it, but in terms of figuring out the maximum value, it's easier to multiply here, so we get 9. Right. And what's the maximum value? What's the maximum value? I'm sorry, what's the minimum value? What am I saying? What's the minimum? Yeah. 9, right? Yeah, right? So you can see that this is the unit parabola. If you wanted to graph it, it's shifted over by 1, it's multiplied by 2, right? So it becomes kind of skinnier, right? And then it's moved up by 9. Okay. Okay. Any questions about that? Yes, ma'am.
So in the previous step, we subtracted 1 from x minus 1 squared.
Yeah, that's because this because of the completing the square, right? We've got x squared minus 2x, right? And that turns into x minus 1 quantity squared minus 1, because when you do this thing, right, you're going to get x squared minus 2x plus 1, right? So I need to subtract off of 1 in order to have these things equal. Yes, Amy? Yeah. You shifted up by 9, yeah. So I just didn't want to do it because I have to draw it up here. Yeah. Okay. But you're right, you shifted up by 9. Oh, yes, please.
So 9 is the max.
9 is the min. I'm sorry, I misspoke. This thing doesn't have any max, unless you restrict it to some domain. Yes.
The dilation of 2 stretch it.
That's right. It just stretches it vertically. So just think, right? We have a parabola, x squared. Right? If we make another parabola, 2x squared, then all the y values get multiplied by 2. So like this guy here, its y value will be here now. This guy's y value will be up here. Right? This guy's y value will be doubled, right? So it's going to look like that. Right? It's going to look like that. All the y values get doubled.
And then when it's shrinked, is it inside the parentheses? Like, is it quantity 2x minus 1? Like, sorry, like f of 2x.
F of 2x. Yeah, so if I had, yeah, that's kind of a funny thing. So yeah, that's kind of cool to think about, right? So I have this parabola, f of x equals x squared. Okay, right? I have this other parabola, g of x is twice f of x. Okay, or maybe 4 times f of x. Okay, so I got 4 f of x. So that would be if I stretched everything by 4, right? So this guy gets multiplied by 4. This guy, I can't do it, it's too close. So yeah, it's going to go up like this, right? Okay, but what if I make a parabola like this, where it's f of 2x? Well, then I would shrink time by 2, right? Time would be sped up by 2, so everything would move inwards this way. And in fact, you get actually the same thing, right? Because f of 2x is 2x squared, which is 4x squared, right? This guy was also 4x squared. So it's kind of cool for a parabola, dilating vertically corresponds to some dilation horizontally. Yeah. So that's not true for all functions. Yeah, but it just so happened in this case that happens. I'll give you one on the next example. Cool observation. Cool thing to bring up at least. Okay. Okay, so I was gonna talk about one other thing, but I think I'll skip it, and if I have time, I'll get back to it. In the notes, it's called the hyperintelligent child's observation. Hyperintelligent child's observation. Sorry. Okay, so I'm going to go to section 4.4 actually, rather than do section 4.3. And so this is, I have the title of this in my notes is expressing something as a function of something. Okay. So, this is kind of a step towards applied math. Okay, so in applied math, what you do is you take some sort of real world situation, and then you translate it into the mathematical world, right? You make some sort of mathematical model of it. Okay, and then you use your mathematics in the mathematical world to do some observations about the thing in reality. Okay, so okay, so let me give an example of what we'll be doing in this section first, and then I'll sort of explain the procedure. Okay, so here's an example. So there's a circle, and the circle has diameter 8, so diameter 8 centimeters, and you have a rectangle inscribed in the circle. Okay, so rectangle inscribed in the circle. Okay, and what you want to do is express, the question is express the perimeter of the rectangle as a function of its width. Okay. So you see, here's the width of the rectangle, right? The diameter of the circle is 8. The width is this thing, and you notice that as the width changes, the perimeter of the rectangle changes. Right? 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 As the width changes, the height is also going to change. Right? Perimeter, I hope you remember, perimeter is just the sum of all these lengths. Right? It's the total length, the total of the side lengths of this rectangle. Right? So express the perimeter of the rectangle as a function of its width. So, okay. So what we want is So you think, okay, we want the perimeter, right? P, let's call that P as a function of W. Okay, right. We want to express P as a function of W. So if I write something like this, you read it as P is a function of W. Okay, P can be realized as a function of W. We want P as a function of W. Okay, so you think about, say, okay, well, what's P? Well, P is going to be, well, it's going to be twice the width, and let me just put some names on these things. I'm going to call this thing the height, right? I'm going to call the height H, right? So let W denote the width, H denote the height, right? And then P is going to be 2W plus 2H, right? In terms of those things, right? So yeah, this is not what we want because we've got P as a function of W and H at this point, right? Right now P is a function of two variables. Okay, we really want it to be a function of one variable. Okay, but what you notice is that W and H are related to each other, right? W and H are related to each other. As W changes, H is forced to change, right? They're kind of stuck to each other. As if I know what the W is, I actually know what the H is, right? So H is actually realizable in terms of W, right? So you notice that there's a relation, actually, a relation between H and W, right? If I know what W is, I know what H is, right? So this is 4, right? Because the diameter is 8, right? And this thing here is W, right? This is W, and this is H. Does anybody see the relation between W and H? Really? Lisa? It's half of what H is? Well, in my picture, yeah, but let me change the picture a little bit. It's W, and here's H. Right? Or this could be W and this could be H, right? So the ratio is not some constant, but there is some relationship between them, right? Anybody see it? Janie?
Is W plus H the diameter of the circle?
No, because think, I mean, just look at it. You know, if I move H over like this, that's a guess, but the hint, what is this? What is this thing here? Stella?
I don't remember exactly, but doesn't have formula like square root of like it's like the half of the circle formula, like the square root of x plus h squared plus x plus. Don't remember the other variable, but you know, like the half circle formula.
So it's simpler. It's simpler than that. What's the equation for this thing right here? This thing is a circle, right? What's the equation for a circle of radius 4? Who's talking? I can't tell. Yes, Brisa.
Is it radius squared? C equals radius squared.
So what's the equation for a circle of radius 4? Those of you who've been in the class, who were in class 2 weeks ago? What's the equation of a circle?
The circumference. So 8.
What's the equation for a circle? For a circle, like if I have a circle and I have some point x y on it, what does this x y satisfy? So the radius is say r. Zoe?
The x minus x
So this is 0 here. So.
also x squared plus x squared equals
Right? So here you got the circle, it's a radius 4, so you know that x squared plus y squared equals 4. Right? X squared plus y squared is 4. This should look familiar, very familiar. I hope I'm misreading the class. You look like you've never seen this before, but I'm hoping I'm misreading you. Right? X squared plus y squared equals 4, right? So what does that tell you about w and h? Well, what are the coordinates of this point here? What are the coordinates of this point? If this is w, this length is w, what's the x coordinate here? Aaron?
Is it 4 squared?
I'm sorry, 4 squared. Yeah, thank you. Maybe that's why you all looked confused. Thank you. Okay, so if this length is w, what's the x coordinate of this point here? Okay, take a minute and see if you can figure out the x and y coordinates of this point. Okay, talk with your neighbor. Actually, that is not h, right? Sorry, I made a mistake. This is h. Sorry. This thing is h here. This is w. Sorry.
Does the rectangle have a center of 0?
Yeah. So it's this rectangle here. Okay, anybody figure it out? If you didn't, that's okay. Anybody want to try? Yes, Vivi.
What I was thinking is that the coordinates were 1/2 w, comma 1/2 h.
Exactly. 1/2 w, 1/2 h. Right? Because this is w, right? So this is going to be half w. Right? This is h. This is 1/2 h. Right? Okay. So what do you see? You see that 1/2 w. So 1/2 w squared plus 1/2 h squared equals 16. Right? Because it lies on the circle. Right? This length is 4. Right? So Pythagorean theorem, right? 1/2 w over 2 squared plus w over 2 squared plus w over h squared equals 16. Right? Or distance formula, which is the same thing. Right? And so what do you see? That h, let's multiply it out, I guess. W squared over 4 plus h squared over 4 equals 16, right? So w squared plus h squared is equal to 64. In other words, h squared equals 64 minus w squared, or h is the square root of 64 minus w squared. Okay, so there is a relation. You can actually you can actually express h in terms of w. Okay, and then coming back here, right? We wanted to express the perimeter. We wanted to express the perimeter only in terms of w. So what we do is we got this expression for h in terms of w, so we just substitute that in. So we can write perimeter is going to be 2w plus 2 root 64 minus w squared, right? And that would be the expression. Maybe I should not have chosen that as the first example. In my notes, I was thinking this morning, should I do this as the first example or not? And now I see that was probably not the that could have been the second example, right? Not the first example. Let me do another example. Okay, I'm going to do a simpler one here. So let's start off with let's restart with another example. Okay, so here is example, let's call it example 7 in my notes, or example 1. Okay, so two numbers sum to 8. Okay, express the product. Express the product as the function as a function of one of the numbers. So, same sort of thing. You start off by, the other one we started off with a picture. I don't know if you want to have a picture for this one. You could. You could say, you've got this length 8, and you've got two numbers, right? X and Y. So, and they sum to 8, right? So, right, you start off with some picture, and you notice that one of the first things I do is put some variables on it. So I'm going to call the first one X, I'm going to call the second one Y, right? And I want the product, right? And you see that the product is XY as a function of just one of the numbers. Okay. So you want to express it as a product, as a function of X, say, right? So you want the product as a function of X. Okay. Well, what's the relationship between X and Y? Vivi? X plus Y equals 8. So you notice that there's this relation, right? X plus Y equals 8, right? So if you know X, you know Y, right? Right, Y is just going to be 8 minus X, right? So, so same sort of thing. You want the product, maybe initially the product you think of as a function of both variables, but then you realize that one of the variables is related to the other variable, right? Y is just 8 minus X. So we can get rid of it, right? Y is just 8 minus X. Right? And then we realize that it's just a function of one variable rather than two. Okay. So this section is basically realizing, getting something complicated, and then realizing that it's actually a function of one variable. Okay. That's the whole game of this section, which is you have some sort of situation, and you're trying to realize something as a function of one variable. It appears to be a function of more than one variable, but then you notice some relation, and then that allows you to get rid of the second variable. Okay, that's basically the game that we're playing here. Okay, so just like what we did here, right? The perimeter, it's easy to describe the perimeter. The perimeter was, twice w plus h, but we want it as a function of one variable, and then we noticed that, oh look, this thing lies on the circle, so that means that there is a relation between the y value and the x value, right? The y value has to be the square root of the radius squared minus the x value squared, right? Right, and so we can throw that guy out and replace it with using that relation. We can get rid of it and realize this thing is a function of one variable. So roughly speaking, there's a process, and the process goes like this. One, draw a picture. That's not really a process, but it's sort of useful to help you see things. Okay. Two, state specifically what is desired. Assigning variables to significant quantities. Three, write down any relation relations between the variables. And then four, try to eliminate one variable. From the desired function. Okay, so right, like in this one, the product involved two numbers, but really we could get rid of one of them, right? Here, the product involved two variables, but really we could get rid of one of them using the geometric observation. Okay. So these problems are mainly going to involve some sort of geometric observation. X plus y equals 8. Right? I guess it's an algebraic observation. Here, w over 2 squared plus h over 2 squared equals 16. So some geometric observation that you turn into a algebraic observation. Okay. Okay, let's finish with one example like this. So here you're given a piece of wire. And the wire is 14 inches long. Okay. And you break it in half, you cut it in half, and you use the part on the left to make a square, say. And you use the part on the right to make a circle. Okay, so this part becomes a square, and this part becomes a circle. And actually, let me do it the opposite way. So this one on the left becomes a circle, this one on the right becomes a square. And I want you to express the total area in terms of the length used for the circle. Okay, so let's call that guy X. Okay, then you want to express the total area in terms of X. So let's say total area is we're gonna call T. We want T as a function of that length X on the left. Hey.
When you said this cut the wire in half, do you mean like exactly one time?
No. You just break the wire at length X. Yeah, X is any number between 0 and 14. Sorry if I said half. I didn't mean half. Just break the wire. Actually, let me do this one because we're actually already over time. So let me just do this one quickly. Okay, so let's call, if this length is X and this length is Y, then what's the area of Y? What's the area of the square here? What's the side length of the square? Right. Y over 4, right? So the area here is going to be y squared over 16, right? Okay. Now, we've got this circle, and what's the area of the circle? Well, to do that, we need to figure out the radius, say, right? The perimeter is X. That's the area of the circle. The perimeter equals X. What's the perimeter in terms of the radius? Anybody know? Anybody know the perimeter of a, if you have a circle of radius r, what's the perimeter of the circle? Pi times the diameter, and so 2 pi r equals X. Right? So that tells us that the radius is going to be X over 2 pi. Right? So the area, what's the area of the circle? Area of the circle is going to be pi r squared, right? Pi r squared, so you get pi times x squared over 4 pi squared, okay? Which is x squared over 4 pi. And so the total area is going to be x squared over 4 pi plus y squared over 16. Okay. But we can realize y in terms of x, right? What's y in terms of x? X plus y equals 14, so y is equal to 14 minus x, right? So we get x squared plus 14 minus x, quantity squared would be 16, right? And so that's the total. That would be the area in terms of x. Okay, I'm sorry, I've really kept you over time. Yes?
I was wondering if you consider moving the deadline for this week's homework until after fall break.
Oh, yes, it'll be due on Wednesday,
On
not,
Wednesday.
yeah, not Monday, yeah. Thank you for reminding me. Yes.